In our previous video, we looked at an example of a calculation to determine the equivalence point that we expect a weak acid, or that was actually a weak base, and a strong acid um, would reach. And we used it to pick an indicator. Um, so now I want to actually step out further and think about the entire titration curve of something that is a weak acid or base with a strong base or acid. So right now I have a graph in front of us that's showing the titration of a weak acid with a strong base. So we're starting at an initial pH of a weak acid that's below 7. And so that means it's in the flask. We have a known strong acid in the burette that's being slowly dropped. So we can see the volume of sodium hydroxide on the on the x-axis, showing the addition of sodium hydroxide as we go. So what we have in this titration is we have just our acid alone. So it's like just our acid. And so we can predict what that pH will be just from knowing the concentration of that acid if we do and the amount we have. But we might not have that information if it's unknown. So we're going to use our pH sensor to learn it. Then we're going to slowly add sodium hydroxide. As we do, our weak acid, so in this region right here, we're going to be adding to our acid, and I'll use just generic terms here, like HA is acid. Let's do NaOH. Is going to completely react. So all of that hydroxide ion, being a strong base, will react with our weak acid, form some A-, our conjugate base, and some water. So as we add sodium hydroxide to our weak acid, we're converting our weak acid into its conjugate base. All of that sodium hydroxide is reacting. So at any one of these points here, let's just take this point right here, we have some acid around and we have some conjugate base from that acid, but we don't have any hydroxide ion because all hydroxide added will react with the weak acid to form the conjugate base. So we just have these two things. And as we add more sodium hydroxide, we're going to see that conjugate base concentration increase as the weak acid concentration decreases. And so there's this period before we hit the equivalence point where we are converting weak acid into conjugate base. And it takes a while. And during that time period, if you look at this, the pH doesn't change drastically at all. So when we have a weak acid present with its conjugate base, that is our buffer system. That's exactly what it is. And so this whole region right here is a buffer system. And it is increasing the amount of conjugate base. And so it's becoming a better and better buffer until we hit this magical point right here, where we have the same number of moles of our weak acid and its conjugate base. And so this is the definition of a good buffer. Then as we add more sodium hydroxide, we're going to keep increasing that conjugate base concentration. So our buffer gets better, it's the best it's going to be, and then it starts getting a little bit worse until we get close to the equivalence point. We see a dramatic change in pH. One could say we've reached the buffer capacity until we hit that equivalence point where we've converted all of our weak acid into conjugate base. So right here, we have a lot of A-, right? And that's about it. Unless that conjugate base, right? So thinking about this can react with, with water and form the weak acid that we actually started with. And so that equivalence point is actually going to always be, if it's a weak acid and a strong base, it's always going to be at a slightly higher pH than pH 7, because that conjugate base will react with water to form a hydroxide ion. And so that equilibrium will have some of our weak acid around and some of our conjugate base. So at that point, we don't have all conjugate base and nothing else, but a balance of the two based on whatever the equilibrium constant is. Now, as we keep adding sodium hydroxide, then what we're going to see is that the solution becomes very basic very fast. And so here we have an excess of hydroxide ions. So that increases our pH. When that happens, thinking about our equilibrium that was at the equivalence point, we're really increasing this as we add more sodium hydroxide. That's going to shift our equilibrium to favor the conjugate base. We'll see very little, none of our weak acid around. We'll just see conjugate base, and we're going to see lots of hydroxide ion. So that's kind of our weak acid, strong base titration curve. You could do this kind of same process for a strong acid, weak base as well, and you'll see a similar pattern. So here is kind of a summary of some more information about what we just talked through in general terms. So when we start out, our initial pH is going to be determined by that Ka of the weak acid, because we don't have anything else around. As we go through our titration, we're going to hit this buffer region right here, where the pH would be determined using our the equations that we're going to use for buffers, our Henderson-Hesselbach or Clausian-Clapeyron. I'm getting them mixed up, but it's Henderson-Hesselbach equation. And so we can calculate it, the exact pH of our solution there, using the same tools that we use to understand what the pH of a buffer solution would be. Now, there is one special point here, and it's the point smack in the middle. I call it, I don't call it, everyone calls it the half equivalence point. This is the spot where you've added exactly half the volume of the sodium hydroxide that you need to reach the equivalence point. This is also where those moles of weak acid are equal to the moles of conjugate base, as we show here that the concentration is the same of both. And at this point, we have this really easy calculation. The pH is just equal to the pKa of that weak acid. So you're like, oh, I know the Ka of this weak acid. I can look it up in a table. The pKa of it is the pH of our titration at that point. Moving on, our equivalence point pH, we've already done an example of how to do this, but what this is going to require a bit of work. It's going to require learning what the concentration of the conjugate base of the weak acid is. In this case, if we were doing a weak base with a strong acid, we would find out the conjugate acid of the weak base. So whichever one is the weak one. So we're going to figure out that concentration at the equivalence point. That's going to be our initial concentration in an ice table. And we're going to use that to determine the pH of the solution at the equivalence point, which is a lot of steps. It's a fair amount of work. After that, we will, if we continue adding sodium hydroxide, we know that that strong base is going to dominate the pH value that we're reading. And so here, that excess concentration, so you have to figure out the excess concentration of hydroxide. So how many moles have I added more than what I needed to reach the equivalence point? Divide that number of moles by the volume. That excess POH you can use to calculate the POH to get to the pH of the solution. And so we expect you to be able to do calculations at any of these points along the way, be that the initial the half equivalence point, any of the points in the buffer region, equivalence point, and anything after the equivalence point. And these are skills we've been working on all quarter. It's just equilibrium, it's just acid and base, and I don't just, but it is taking a lot of things and putting it all together into one. Here's a summary again, just to kind of help with problem solving strategies. If you need to find the initial pH, calculate the problem like a weak acid equilibrium problem. So you're going to need an ice table. The pH before the equivalence point, you're going to use the Henderson-Hasselbalch equation. This is a buffer problem. At the equivalence point, this one is really a solution stoichiometry plus an ice table plus a pH calculation. It's fun. The pH beyond that equivalence point is a stoichiometry problem. Plus a pH problem. You don't need to do the ice table for this one because that hydroxide is such a strong acid, it's going to dominate everything. It'll shift our weak acid equilibrium to favor the conjugate base. And so you're like, whatever number of moles of OH I have, I'll just divide that by the volume. That's my concentration. I'll use that to calculate POH and then pH. Or use it with the KW expression to figure out the hydronium ion concentration and calculate pH from that. All right, so the next video is going to walk through an example problem. It's a lot. So it's going to do a calculation at each one of those steps. I even added in a little extra bonus one of looking at another point within that. So then the next video is really just going to be walking through these types of calculations you do around a weak acid or weak base titration problem.